for a couple of weeks. So, the general framework is simulation of hydrologic data and simulation by using statistics and probability. So I introduced the concept of probability distribution, and we took into consideration basically the Gaussian distribution and the uniform one. And I showed you how we can generate by using R or by using even less, let's say, less evolved programs, how to generate outcomes from the Gaussian distribution. And the basic concept that I stressed to you is that the generation of random variables can be done by just sampling, so taking outcomes from a probability distribution. But I said that when we consider families of random variables, so not just a variable by itself, but groups of variables, and you can use the term families, then I said we need to make use of the theory of stochastic processes. And therefore I introduced to you the stochastic process, which is a family of random variables. And I said that from a physical point of view, from our point of view, using stochastic processes, so using groups of random variables instead of just one, we have the opportunity of taking memory into account. And therefore I said that when we want to generate river flow data, or when we want to generate data that are affected by memory, we can't use just the notion of probability distribution. We have to consider a group of random variables, therefore a stochastic process. So first of all, keep in mind the definition. A stochastic process is a family of random variables, which means that you are passing from just one number to a group of numbers. And by considering a group, then you are allowed to take memory into account. Fine. And then I said, I introduced two important properties of stochastic processes, stationarity and ergodicity. And for ergodicity, I just said, let's say that it's a property whose definition is a bit complicated. I don't want to give the full definition, the formal definition to you, but let's say that it's a property that allows us to derive the statistical properties of stochastic processes from a short sample of data, from one realization. Stationarity, I said the process is stationary when its statistical properties do not change over time or position. Usually stationarity refers to time. So let's say that the statistical properties do not change over time, which means that if you get like river flows, if you compute the average value, mean value, over a time window, like let's say 1910, and then you move forward 30 years and you compute again the average value, you find more or less the same value. Of course, you won't find exactly the same value, because when we talk about statistics, usually we talk about real numbers, so you don't find the exact value, but still you can judge by your intuition if the statistic is not changed. So if you can assume that it didn't change, then it means that the process is stationary. And let's say, once again, that these properties are properties of the process, so the model that we use to model the natural phenomena. And they are not properties of the natural phenomena itself, just the process. So we can't really say that a time series or the river flow in a given river is stationary. It's the model that we use to represent it that is stationary. Okay, this is not really, doesn't make a big difference from a practical point of view, but from a, let's say that assumptions are usually introduced on the models that we use for reproducing a process, because it's more correct to say this. Okay, and then I introduced the autocorrelation function, and I said, first of all, I gave to you the relationship for computing the autocorrelation coefficient, and then I said you can plot this function for increasing lag values. Here the lag is indicated by the letter key. I think I used L in when writing at the blackboard, but it doesn't make a big difference. Now I want to show you how in R we can compute the autocorrelation function. We have a routine that allows us to easily compute it. And let me just try to show you it. But let me go, first of all, where I have a time series of here. I think here I have a time series of the poor river. Let me see. Now I increase also the fonts. Okay, I think it's. Oh, okay. Here I have a time series of the daily river flows of the Po River. Now let me increase the fonts. Oh, sorry. Okay, and it is called here Po, and it's you see 26,000, almost 27,000 of data, which means if we divide by 365, almost 70 years. It's taken from 1920 to 2010, and if we plot it, let me see, plot. These are just the numbers as they are measured. Maybe that the hydrographic service made some corrections because sometimes they make some checks and then the result is that there are many series of the Po River around. Some of them are a bit corrected, so they are not really identical, but more or less the numbers are indeed the same. This one, apart from the checks that have been done by the hydrographic service, the National Hydrographic Service, this one is unchanged. They didn't make any transformation to it. So let's see this time series, and let me put a line to show it to you. And also color, let me put the red, because it makes the graph more appealing. Okay, so why? Let me see, reading configuration. Let me see. Doesn't work. Ah, no, it was there, sorry. So, follow. Ah, okay.
We use a comma, like not double English.
Let's see. I don't think it's a problem. It was there then. So what is the matter? Let me see. Because this is device 2, so okay, it was just a problem because I had to enlarge the graph, the window. So this is the time series. It's not really easy to understand, but you see the maximum is, these are mean daily data. So the maximum is about 8,000. Actually, the peak flow, for instance, in 1951, which I think it's this one, and I would say 10,000, let me see, 10,000 is about less than half. No, maybe, okay, I'm not sure. Anyway, the peak flow is much higher than the average value, because the peak flow of the Po River at the closure section, which is Ponte Lago Scuro, it's about 13,000. But if you look at the daily average, then you get less. Okay, and let's now have a look at the autocorrelation function of this series. And looking at the autocorrelation function is very easy. There is a routine, let me just, sorry, which is called ACF, and I can do this, and it's better to specify a lag. So lag that max, let's say 20 days, and there is something in this series. So, just 1 second, I want to see. Okay, because there are some NA which are not assigned, probably because there is some missing value. So let me see what I can put. I don't remember the instruction for telling this function that when it finds some NA should not fail but skip them. Okay, and yeah, pass. Yeah, pass. Let me see. Let me try once again. Let me see. Okay, so that's now I am defining this series as a time series. I'm not sure I already told you how this can be done, but probably in order to compute the autocorrelation function we have to tell R that this is a time series and the instruction is TS, and it wants to know the frequency. The frequency is if the time series is periodical, we have to put the frequency, which is indeed, this is the period, not the frequency, but it wants the frequency specified in this way. But there is still something which doesn't work. So, I don't understand, because I just upgraded R, maybe. Let me see. Just trying to transform the series and see if... Okay, now it seems... There is something here which is still just a second. Okay. Okay, I turned to the time series of the Po at another closure section because I had some problems with Ponte all'Oscuro. This is a typical autocorrelation function. You see that it starts from 1, and you can see that it's decreasing, of course, for increasing number of days. And another issue that I want you to notice is these two blue lines around the zero values and around the zero value. These two lines are called the confidence bands of the zero value. It means that if all the autocorrelation coefficients but the first one are inside these two bands, it means that we can assume that the autocorrelation is 0. And this assumption is satisfied at with 95% probability, because these are the 95% confidence bands. So basically, I will explain you later how they are computed. It's very simple. But basically, and I can tell you just now, the weight of the confidence band at the 95% confidence level is plus minus 1.96 square root of 1 over n. This is the width of the confidence bands at the 95% confidence level. Again, what does it mean this? It means that if a single autocorrelation coefficient is included inside this interval, which is an interval that is centered around the zero value, you can assume that the autocorrelation coefficient is 0. And the test gives to you a 95% of confidence, meaning that you have 95% probability that your assumption is satisfied. This definition that I gave to you of confidence level is not formally correct, but it's, from an engineeristic point of view, I believe it's understandable. So let's take it. This applies to any individual coefficient, which means that if I got all the autocorrelation coefficient inside this band, but the first one, because the first one for definition is, by definition is 1, then I could assume that the series is independent, no memory. I can tolerate that I can assume that I can take this assumption verified even if 5 over 100 coefficients are outside the band. Because given that the test is satisfied with 95% confidence, of course, if I get 5 over 100 of them, of the autocorrelation coefficients, which are not included in the confidence bands, still, I can say that the assumption is likely to be satisfied. In this case, we were not expecting that the coefficients were close to 0, because of course we know that there is memory in this time series. But this is, anyway, a test, in general, to check if indeed there is memory in the series. Okay. Now let me show you. I'm just looking. I don't understand why the original series doesn't. Ah, yeah, because it was. Oh no. I don't remember. There must be a reason in the data, and maybe it is. But anyway. Now let me show you the same autocorrelation coefficient. This is another, as I said, the same autocorrelation function. This is another, as I said, time series of the Po River at Piacenza, not at Ponte Lagoscuro, but at Piacenza. And let me show you this one, which is more or less similar. Let me see, because I don't understand. I think. Okay, I have to open and close the graphic window every time. This is more or less the same time series than the one that I showed you before, with one difference, that this is the original one. The one that I showed you before, it was deseasonalized, and now I explain you later what it means. This is the original series. Let's see what happens if I plot the autocorrelation function for a longer cluster of lags, for increasing lags. So let me show this, and let me write lag.max. And let's put 1 year, or maybe 2 years. Okay, so you see this strange effect. So let's try to understand why. And first of all, let's see, there is, what is the behavior of this autocorrelation function? It's periodical. Now let's try to understand why it is like that. And the periodical means that you have a peak in the autocorrelation function after 1 year and after 2 years. And then you have a secondary peak after about 6 months. And you also have some negative peaks after, let's say there is a negative peak after 9 months, and then here you don't see a negative peak, but you see that there is a minimum in the autocorrelation function every 6 months, 6 months again, because this is 9, this is, let me see, this is 12, this is 18, no, this is 15, yes, 9, 15, and 21, yes. So after, and in 6 months you see peaks in the autocorrelation function, either positive or negative. The first one is not negative, but still it's a minimum. You see that it's a minimum. Now let's try to understand why. And let's, first of all, remember how it's done typically in the time series of the Poor River. How it looks. So if you plot it QT for 1 year, from 1 to 365, what you see is basically a minimum in the winter, and then a peak in the spring, then you have another minimum in the summer, and then usually an higher peak in autumn. So what you see is that every 6 months you get similar river flows. Every 6 months. Every 6 months you have 2 peaks, and every 6 months you have 2 droughts. What means similarity? Similarity means that if you look at the memory of the series, it looks like there is memory. And indeed there is memory, because, you know, if the river flows are very low in winter, and then you have, again, low river flows in summer, they are related. There is memory, meaning that the river flow of summer is more or less related to the river flow of winter. And let's take a broader interpretation of memory. Memory in this case is not given by the fact that the river keeps memory, it's the weather that keeps memory. And keeping memory doesn't mean that the weather is similar. It means that produce similar effects in terms of river flows. So memory is not just given by the fact that the river remembers. If you look after a couple of days, after 10 days, indeed the river remembers itself. If you look at a time span of 6 months, the river doesn't remember. But still there is similarity, which is given by the fact that some general behaviors are similar to themselves. So strictly speaking, the term memory in this case is not the correct term. We should say similarity. The autocorrelation function gives an interpretation for this similarity. And of course it is treated like a memory. I hope you understand the difference. Because, you know, we cannot say that the Poor River keeps memory of its condition 6 months before. This is not what this autocorrelation function says. Maybe that indeed it keeps some memory, but this autocorrelation function just tells you that the river flows are similar every 6 months. And so you see this up and down. And you may ask me why the first minimum is not negative. Just because the first minimum is influenced by the very strong memory in the short term. So the river has a positive memory which lasts for some weeks, and this positive memory basically induces a mitigation of the negative peak of the autocorrelation function. So the autocorrelation function is a powerful tool to look at a time series and to get its general behavior. For instance, if you look at the time series of the Nile River, you wouldn't see such a 6-month periodicity. You would just see a 1-year periodicity. Because in the monsoon, in the climate dominated by monsoons, there is only one period. There is only one peak flow time during the year, not two. So you see that by looking at the autocorrelation function, you indeed get some information, and you see that it's very easy to compute. Okay, that's fine. Let's go back now to our PowerPoint presentation. And let's move forward. This is an example of autocorrelation function, and there is not much more to do. And now, let's now move to the definition of the model that we can use for generation. So far I talked about stochastic processes. I provided a definition, but I didn't give any anticipation of the mathematical structure. Because of course, if we want to keep this memory into account, let's continue to call it memory, then we need a mathematical model for the generation, which is not just done by sampling from the probability distribution. We have to introduce some more. And this some more is the stochastic process, and we have to provide a mathematical definition for it. And you will see that the mathematical definition is very simple. In contrast with the theory, that it's a bit nasty to learn, you will see that the mathematical definition is very simple. And let's make, first of all, an assumption. And the assumption is that the dependence structure of the considered process can be represented by a linear relationship. Meaning that memory, this is a complicated sentence. Let's make it very simple. We have a need. The need is to reproduce with the mathematical model this memory of the river. So the fact that I go today and I see the river flow, and if I go tomorrow I see a similar river flow, I need to introduce a relationship, a mathematical relationship explaining this dependence. And this mathematical relationship is a deterministic relationship. And let's assume that this relationship is linear, meaning that I assume that I can express the river flow of tomorrow as a linear combination, a linear function of the river flow that I observe today. And why do we introduce this linearity assumption? First of all, because it is simple. It's a simple function. The linear function is very simple to deal with. Second, we assume this linearity because we know that the probability distribution of the river flows is to be preserved. So we said that there is a problem when we combine, we transform random variables, that we get as a result random variables that do not have the same probability distribution. In this case, we have a problem because the random variable is river flow, and the probability distribution it's always the same because we assumed that there is stationarity in this process. So your question could be, why do we need to assume that the process is stationary? We need to do so because if we want to look at the past and make inference for the future, we necessarily have to assume that the river flow is stationary. Meaning that, I want to project the same statistics into the future, I need to introduce an assumption of stationarity. Stationarity means that the probability distribution doesn't change in time. And this helps me because otherwise I would make inference on something that happened in the past, and if this something is going to change in the future, it wouldn't be any helpful, this statistical analysis on past data. I want to assume stationarity, meaning that the probability distribution shouldn't change from today to tomorrow. So basically I need a mathematical relationship which transforms a random variable, but the result should follow the same probability distribution. And you know that I need two conditions for this. I need to assume that the random variable is Gaussian, and I need, second, to assume that the transformation is linear. Because I already told you that the only probability distribution that keeps unchanged after a linear transformation is the Gaussian distribution. So we need Gaussianity, linearity. So let's assume linearity, and implicitly, I will tell you later, explicitly this assumption, implicitly, I already assumed Gaussianity. Let's not to discuss and let's not worry about the fact that these distributions, these assumptions may not be satisfied. No problem. Let's, for now, introduce the assumptions that we need. So the first is stationarity, the second is linearity, and the third is Gaussianity. Fine. Then, if we assume that the process can be expressed by a linear relationship, what does it mean this? It means that I can write, let me use the same formalisms, xt, where x is my random variable, for instance, today, can be written as the product of a coefficient, which is constant, times the same variable that I observed yesterday. To make it more general, let's also put more terms here, with the only condition that they are linear. So let's put plus v2 x t minus 2 plus x phi p x t minus p. This is a linear function, so it's okay. The linear function, I'm not sure I already defined that. Yes, I think so. I already told you the condition, the necessary condition, necessary and sufficient condition for a function to be linear. Basically, it's f ax equal afx. Okay? Fine. This is a linear function. If you make a check, you see that the two conditions are satisfied. But it's not finished. I have to put a plus here. Plus. Because you know, this is a random variable, which it's not clear from this relationship, because this relationship instead is deterministic. So basically I need to introduce a random term here. And the random term, let's call it epsilon t. And you may say, but why do I need to introduce this random term? From a practical point of view, I may tell you that this is an error, because this relationship is not, of course, is not precise. And therefore you introduce an error. And in statistical terminology, this error is a random term. But pay attention. What is the reason why I introduced this linear relationship? It was to explain the memory. So, if the assumptions are satisfied, meaning if the relationship is correct, this random term shouldn't have any memory. And therefore, the situation becomes much simpler, because this epsilon, you can treat it as a random variable. It's not a stochastic process, it's a random variable. Or let's say, it's an independent process. You don't have any memory anymore here, which means that you can sample from the probability distribution, from its probability distribution. If you want to generate this, you can just sample from the probability distribution. And this is a necessary condition, because you know, you introduce all this complication, which means a linear relationship to explain the memory. If at the end you have an error term which still has memory, then we wouldn't solve the problem, because we would have to explain this random term with another stochastic process with memory, which means, you know, it's a nested solution which wouldn't be okay. So let's say that the fact that this epsilon is independent is one more assumption that we are making in order to make sure that everything is correct. Okay, good. So, let's now, for simplicity, refer to the simple case of the autoregressive. This is called autoregressive stochastic process. And it's all the acronym with which it's usually indicated is ARP, where P is the autoregressive order. Now, for simplicity, let's refer to the AR1 process, which is very simple. It says that xt is equal to phi1 xt minus 1 plus epsilon t. I just eliminated the autoregressive term beyond the first order. So let's, in a way, summarize